This is section 2.2, and it's about functions and graphs. Now, the concept of a function is very important and very powerful, and it is, one of the most fundamental tools of mathematics. So this is why the section may be a little bit longer than the others. But we have 5 objectives here for section 2.2. Number 1 is to determine whether a correspondence is a function. So in other words, there are correspondences and there are functions. Then the B part is, given a function described by an equation, find the function values, the outputs, for specified input values. And then draw the graph of a function. That's part C. And then there are ways to determine whether a graph is that of a function using a vertical line test. And then last but not least, we'll talk about applied problem-solving functions and their graphs. So in much the same way that ordered pairs form correspondences between the first and the second coordinates, a function is more general. It's a correspondence from one set to another set. And here just some very simple examples. For each student in a college, there corresponds to his or her student ID. To each item in a store, there corresponds its price. To each real number, there corresponds the cube of that number. So these are just some very simple-minded examples. In each case, the first set is called the domain of a function, very important word. And the second set is called the range. So we have the definition of domain and range. The domain is a set of all the input values, and the range is a set of the output values. Each of these correspondences is a function. Because given a member of the domain, there's just one member. Now this is critical. There's one member of the range to which it corresponds. Given a student, there's just one ID. Given an item, there's just one price. Given a real number, there's just one cube of that number. So here the graph shows it in general terms that between a domain and a range, there are kind of lines that indicate the function. Okay? And so here we have for each input value in the domain, there's one output value in the range. And let's look at an example here. Example number 1. Determine whether the correspondence is a function. So here we have one item, and here's the price. Another item, here's the corresponding price, etc. So here we clearly have a function. And here, let's look at that. So here, the number 3 corresponds to the number 5 in the range. The number 4 corresponds to the number 9 in the range. The number 5 corresponds to -7, and 6 corresponds to -7. So that's a function as well. So this is a yes here, and it's a yes here also. Let's look at example H. So here we're looking at the Chicago Cubs and Chicago White Sox. Aha. So now we have one input that corresponds to 2 different outputs. That means this is not a function. Even though the other ones is only 1-to-1, one Baltimore to Orioles and San Diego to the Padres. But this is not a function because one input corresponds to more than one output. For example P, here we have the domain, we have the Cubs, the White Sox, the Orioles, and the Padres. And here's the range. So here the Cubs to Chicago, and the White Sox to Chicago, Orioles also to Baltimore, and the Padres to San Diego. So that's a function also. So here's a somewhat longer explanation why three of them are a function and this one is not a function, so you can read it here. But basically, I already gave you the explanation. So here are the official definitions. A function is a correspondence between a first set called the domain and a second set called the range, such that each member corresponds to exactly one member of the range. So this is really important that there's only one. So based on that information, let's determine whether each correspondence is a function. So we have 4 examples to look at. So in the first case, we have the domain as these animals, and then there's the range as their speed. So the cheetah can go 70 miles an hour, etc. And there's a 1 and 1 correspondence, so this is a function. In the second example, A relates to a lowercase a, B relates to C, and C relates to C, but D relates to 2 different ones, so we don't have the requirement exactly one member of the range, so this is not a function. Looking at example number 3, there's a 1-to-1 relationship, minus 2 to 4 and 2 to 4. In other words, it's okay when 2 elements of the domain refer to the same element in the range. Same with minus 3 and 3 to 9 and 0 to 0. And you can maybe even guess that this is a number and this is a square of that number. But it is a function. The last example, number 4, we see right away that here we have a number in the domain, an element in the domain referring to more than one element in the range, so this is not a function. Here again, 9 has 2 elements in the range, so that's not a function. So now we discuss the more general definition of a relation. And a relation is simply a correspondence between the first set called the domain and the second set called the range, such that each member of the domain corresponds to at least one member of the range. So in other words, all functions are relations, but not all relations are functions. To be a function has a stricter requirement. As we saw above here in this definition, to go over that again, a function is a correspondence between the first set called the domain and the second set called the range, such that each member of the domain corresponds to exactly one member of the range. Exactly one, that's what makes a difference. Let's talk about function and function notation. This is really, really critical here, what comes next. For example, y equals 2x plus 3. For this relation, the input, the members of the domain, are values of x, substituted into the equation. So we've done that many times when we wanted to graph an equation. We selected some values for x, computed the corresponding y, and so we had an ordered pair and we graphed the equation. The outputs, members of the range, are the resulting values of y. If we call the function f, we can use x to represent an arbitrary input. And this is read as f of x, or f at x, or the value of f at x, to represent the corresponding output. Now, this is something you really need to understand. I will explain it a little bit more. In this notation, the function given by y equals 2x plus 3 is written as f of x equals 2x plus 3, and the calculations above can be written more concisely as follows. So let me go over that here. So we have f of x equals 2x plus 3. What that really means is that what that number is depends on x. When you say a function of something, it simply means it depends on. For example, if you want to know what the function is when x equals some number, let's say 2, select the number f, or x equals 2, then we write this as f of 2. And what it really means is, what is the value of the function when x equals 2? That's what this means. F of 2 means this. It's an abbreviated version of f of x when x equals 2. And what it means, we simply replace x with the number 2. And then we add 3 to it. Of course, the calculation is trivial. 2 times 2 is 4, plus 3 is 7. So that is the function value. So the value of a function evaluated at a given value for the x input is simply a number. Let me give another example. When there was a time when you went to school, you could say that the arrival at school was a function of when you left home or when you left work. In other words, it depended at what time you left home or what time you left work. So we simply say your arrival time is a function of when you left home or when you left work. So in everyday examples, we use indirectly the word function. We just say it depends on. And so if you think of it this way, I think everything will be much clearer. And again, when you look at this example, y equals f of 4, and that stands really for f, what the function is when x is replaced with the number 4. That's what this means. So we replace x with 4, 2 times 4 plus 3, that's 8 plus 3 or 11. Typically the calculations are not that difficult, but it's just to explain what this means. That's what it means. And similarly, when we replace x with the number minus 5, so that means f, the value of the function when x is replaced with negative 5. Wherever you see an x, you replace it with minus 5. Well, here's only one place in the original equation, but we replace that x with minus 5, and we get the result of minus 7. And f of 0, now f of 0 doesn't mean the function is 0. I mean, sometimes it is, but the value of the function f of 0, what does that mean? It means f, what's the value of the function when x is replaced with the number 0. And again, in this equation, we replace x with 0, so we get 2 times 0 plus 3. Well, 2 times 0 is 0. We only have 3, so the value is 3, and so on. It can be useful to think of a function in terms of a machine. So a machine is here, and it has an input. And let's say an input is x equals 4, and the machine itself says 2x plus 3. So whatever comes in gets multiplied by 2, and then we add 3 to it, and then here's the output. 2 times 4 is 8, plus 3 is equal to 11. So in other words, we have an input and an output to a function. Exercise 5 asks us determine whether each corresponds as a function. So here's the domain, the set of numbers. The correspondence is square each number and subtract 10, and then the range is a set of numbers. So we could write this as f of x equals, we square each number, so x squared, and then subtract 10, minus 10. So if we choose a number like 5, so f of 5 is, we replace x with the number 5, so that's f of 5. And that means we square 5. And so 25 minus 10 is equal to 15. And that's a set of numbers. And we can do that for any number, including 0 and negative numbers. So that is a function, because for any given input, we have a very specific output. No input can give us two different outputs. So that's a function. This correspondence is a function. Number 6 asks the same question. Is this corresponds to a function? So here the input is a set of polygons. In other words, a geometric figure with multiple vertices. And the correspondence is find the perimeter of each polygon, and then the output, the range, is a set of numbers. Well, for any polygon, it has a perimeter, and it can only have one perimeter, so there would be a function. Now the same perimeter may show up again, but for a given polygon in that set of polygons, there's only one perimeter per each polygon. So that is a function also. And then number 7, here we ask, is this a function? The domain is a set of numbers. The correspondence is the area of a rectangle. And the range is a set of rectangles. Let's think about it. So you have numbers like 25 or 18 or 200. And of course, that could be the area of a rectangle. But that same number in the domain, in the range, could be created by a different rectangle. So this is not a function. So next we have a function given by f of x equals 2x squared plus 3x minus 4. And we are asked to evaluate this function for different values of x. So the first one is f of 8. That means wherever we see an x, we replace it with the number 8. So it means 2 times 8 squared plus 3 times 8. Okay, and so that means 8 squared is equal to 64. So 2 times 64 plus 3 times 8 minus 4. So it'd be 128 plus 24 minus 4, which would be 152 minus 4, or 148. Okay, so that's kind of a pattern that we want to follow for the other values of this function. For example, when x equals 0. That's usually an easy one. So since this is our given function, replacing every x with a 0 means f of 0 means 2 times 0 squared, 2 times 0 squared, plus 3 times 0, minus 4. Now 0 squared is 0, of course, and 2 times 0 is 0, so it's only 0 here. And 3 times 0 is 0, so the only number that remains that's not 0 is equal to negative 4. So that is f of 0. Now f of minus 3, minus 5 rather, and for the c part, we replace every x in our original function. Let me rewrite the original function. F of x was equal to 2x squared plus 3x minus 4. So that's the original function. So that means f of minus 5 means 2 times minus 5 squared plus 3 times negative 5 minus 4. So minus 5 squared is plus 25, and 2 times 25 is 50. And 3 times minus 5 is minus 15 minus 4. So that would be 50 minus 19, and it would be 31. Now the last part, the D part, may look a little confusing. What is f of 2a? Well, remember what it means. It means we replace x with 2a. That's all it means. So it'd be 2 times 2a squared plus 3 times 2a minus 4. So that means 2 times, and 2a squared means 2 times a times 2 times a. That would be 4a squared. And 3 times 2a would be 6a minus 4. And so we only have now to calculate 2 times 4a squared. So that would be equal to 8a squared plus 6a minus 4. So let's do exercise 9. In the A part, we have f of minus 6 for the given function of x, 5x minus 3. Again, f of negative 6 means we replace x with minus 6, so it's 5 times minus 6 minus 3, and 5 times minus 6 is minus 30, minus 3 is equal to minus 33. For the B part, here we have g of x equals minus 3, and now we're replacing every x with 55. So g of 55, we say, well, there is no x to replace x with 55 by, so then the answer is simply negative 3. And f of a plus 2 for the given function f of x equals minus 5x plus 8. So what that means, we replace x by a plus 2. So then f of a plus 2 means minus 5. That is minus 5. Now comes x, but instead of x, now we replace it with a plus 2. A plus 2 plus 8. Using the distributive property, this becomes 5a minus 5a. And minus 5 times 2 is minus 10 plus 8. So that then becomes minus 5a, and then there's minus 10 plus 8, that would be minus 2. So the answer is minus 5, 8, minus 2. And for the D part, we have f of x equals 6x minus 7. So then f of a minus h means we replace, wherever we see an x, we replace it with a minus b. So then f of a minus h rather equals 6 times a minus h. Minus 7. And using the distributive property, 6 times a is equal to 6a. And 6 times minus h is minus 6h minus 7. So that's how you compute function values. Next will be the graphs of functions. So our given function is f of x equals x minus 4. So we can choose some values for x. And so, for example, we could choose x as 2. When we replace x with 2, f of 2, then we have 2 minus 4. Okay, let me write this out. F of x equals x minus 4. Then f of 2 means we replace x with 2. So 2 minus 4, and that's equal to negative 2. So that's f of x minus 2. And when we choose x equals 0, then in this expression here, in this equation, we have f of 0. We replace x with 0, so we have 0 minus 4, and it would be minus 4. And let's say x equals, well, minus 2, we could use minus 2. So we replace, in this equation, we replace x with 2, so f of minus 2 would be negative 2 minus 4, and that's minus 6. So minus 6. So then we have the ordered pairs. 2 minus 2. And we have 0 minus 4. And we have minus 2 minus 6. So we've done this before. So let's plot these points. 2 minus 2, x equals 2, y equals minus 2. That would be this one here. 2 minus 2. And then 0 minus 4, we just go down the y-axis since x is equal to 0. And then minus 4 is here. So that's the point 0 minus 4. And minus 2 minus 6, we go 2 to the left. X minus 1 minus 2, and we go minus 1, 2, 3, 4, 5, 6. So that's the point minus 2 minus 6. And then we connect these points. The straight line. And this is a graph of our function f of x equals x minus 4. For exercise number 11, we are asked to graph g of x equals 5 minus x squared. And I selected some values for x, 0, 1, minus 1, 2, minus 2, 3, and minus 3. So let's compute the corresponding function values. So if we look at g of 0, that would be equal to 5 minus 0 squared, and that's equal to 5. So that would be g of 0. Then g of 1 is equal to 5 minus 1 squared, and 1 squared is 1, so 5 minus 1 is 4. And when we have g of minus 1, we have 5 minus negative 1 squared. So that's 5 minus, and negative 1 squared is 1, so 5 minus 1 is 4. And similarly, g of 2 is equal to 5 minus 2 squared equals 5 minus 4, or 1. So that's 4 here. That's 1. And then g of negative 2 would be 5 minus negative 2 squared, and that's equal to 4, because minus 2 times minus 2 is positive 4. We have a minus sign, so 5 minus 4, and that's also equal to 1. And then let me rewrite the formula here. G of x was equal to 5 minus x squared. So when we compute g of 3, would be 5 minus 3 squared, would be 5 minus 9, and that's negative 4. And then g of minus 3 means 5 minus negative 3 squared. And so that's 5 minus, and negative 3 squared is 9, so it's 5 minus 9, which is also negative 4. So then we have the corresponding ordered pairs, 0, 5. We have 1, 4, and minus 1, 4. And we have 2, 1, and minus 2, 1. And we have 3, negative 4. And we have minus 3, minus 4. The next step is to plot these ordered pairs. So 0, 5 would be this point here, 0, 5. And 1, 4, x equals 1, y equals 4. That's this one here. And then minus 1, 4 would be this one here. And then 2, 1, x equals 2, y equals 1. That would be this point here. And minus 2, 1, minus 1, minus 2, 1. This is minus 2, 1. And then the last one would be x equals 3 and y equals negative 4. So here's 3 minus 1, 2, 3, 4. So here's 3, negative 4. And then minus 3 and minus 4 would be minus 1, 2, and 3. Minus 1, 2, 3, 4. And it would be this point here. Minus 3, minus 4. And then we draw a smooth line through these points. So this is a graph of g of x equals 5 minus x squared. And what this looks like at the at the peak here, at the maximum, it looks like this. It does not look like this. It looks like this if it were magnified. Next, we'll talk about the vertical line test for a function. And so here's the important information. If it is possible for a vertical line to cross a graph more than once, then the graph is not the graph of a function. So when you look at this graph here, if the ruler was like a vertical line, then we'd see that it would cross the graph more than once. In fact, in this example, 1, 2, 3, 4 times. So we can conclude that what we're looking at here is not the graph of a function. Okay, so it's a pretty simple concept. Now, for the next few exercises, we're to determine whether the graph represents a function. So we look at number 13, and when we pass the vertical line through this graph here, it intersects the graph in only one point. So in other words, this is a graph of a function. Yes. When we look at number 15, well, we can look at number 15 since it's next to it. So when we use a vertical line test here, we see that the line intersects the given graph in more than one point, in fact in 2 points, like here and there. So therefore, this is not a function. No. And number 14, let's look at number 14. How about the vertical line test here? Well, here everything is okay, but when we get over here, we notice that the line, the vertical line given by the ruler, intersects the graph in more than one point. So this is not the graph of a function, no. And here we can see that the vertical line intersects a given graph in only one point at all, everywhere. So this is the graph of a function. So it's a pretty simple thing, the vertical line test. Okay, the last part is the application of functions and their graphs. And so the graph we are looking at here is the gift card that people purchase. And so that's the given graph. And then the question of point A, or the first part, is to estimate the amount spent on gift cards in 2012. We locate the year 2012 on the horizontal axis, which, by the way, is an important little detail, that in almost all cases, time is on the horizontal axis. And there's a reason for that, because that's also called the independent variable. Okay, so here's 2012, and we draw a vertical line until it meets our graph of the function. And then we move across to the vertical axis. And at that point, it's about 107. So that means about $107 billion is spent on gift cards in 2012. If we ask a similar question for 2016, it'll be the same thing. We draw a vertical line that goes up to 2016 and then go across to where it meets the vertical axis, and there would be about $140 billion. So that's how we can use graphs to estimate the range part here, how much people are spending given a year. In 2017, that's the B part. Again, on the horizontal axis, we locate 2017, and we draw a line across, and there we go to 150 billion. So we can estimate that the amount of money spent on gift cards in 2017 was about 149 billion rather. Now, it can also go the other way. We can also ask the question, in what year did people spend 120 billion on gift cards? So the way to do that is you say, okay, 120 billion is here. So I go over from 120 to the function, and then I drop down to where that might be. And it kind of looks like about the year 2013. That's kind of a guess here. But if I draw a line here from 120 over to the graph of the function, and notice that we aren't given an equation for the function. But if we now drop the line here, it's about 2013. Again, it's an estimate. If you want to know what year the people spent 120 billion on gift cards, so it would be about 2013, approximately. So you can use graphs of functions in more than one way. This concludes section 2.2.